So good day, everyone. So in the previous video, we briefly recalled what linear regression is. And in ordinary least squares, we have a closed form na formula for estimating the parameters beta or theta, actually. So, and we can do this by computing it using this equation. So we have the matrix inversion of the dot product of X transpose and X with the dot product with X transpose again and Y. So this is a very expensive operation, especially when we have a lot of predictors. So supposing we have 100 na predictors, so we'll be needing 100 by 100 na matrix. And this inversion requires at least na n cubed na operations. So that means that we are going to need at least 1 million operations to invert the matrix. So this is not appropriate when we want to use linear regression for a very large data set. It is very costly. So gradient descent is a lot more cheaper alternative in terms of execution times or number of operations, especially when we deal with a lot of predictors. So this is the high level description of gradient descent, and this is also the algorithm that you have to implement. Okay, so it is an iterative na optimization na algorithm wherein you keep iterating, you keep updating the weights until such time that we obtain the weights that are optimal, that will give us the least errors in the prediction. Okay, so it starts with by preparing your data set. Okay, so we have prepare your data into training and testing, and we'll be going to use the training set, right, to obtain the optimal na parameters theta. So we have the predictors x sub 1 to x sub j with a bias with assuming a value of 1. So each of the predictor and the bias will have associated na weight theta, and we are going to take the weighted na sum of the predictors and weights. So we have the beta and the theta naught or theta 0. So since b is equal to 1, we have theta 0, then x sub 1 and theta 1, theta x and theta j and x sub j. So this should be j and not n. Okay, and we are going to take the weighted sum of all this, right? And we can represent it using this equation for all of the instances or for all of the samples in the training set. We take the theta times x. And this is also equivalent to its matrix na representation, theta transpose x. So this is equivalent to this part. So this is very much easier to do or implement in Python, isn't it? So now we can use this formula to estimate a certain response y. Okay, and we simply have to plug in the value of x, value of feature values into our model h, okay, and we can obtain a certain response. And of course, in order for us to evaluate the quality of the predictions, in other words, evaluate the amount of error or how far the actual is from the predicted value, then we can calculate the cost. And we can do that by simply taking the sum of the squared and differences between the actual and the predicted. So this is the predicted. As you can see, this h of x is equivalent to y hat. All right. Take the take the sum of the square differences and divide that by 2m. So this is the cost or the MSE na cost for gradient descent. Okay. So in order for us to minimize this, cost, and we have to find those optimal na theta, and we can do that by computing the weights, nudging the weight a little bit. Okay, so now we can compute the new weights using this formula, and we have essentially taking the difference between the actual and the predicted multiplied to the feature values and take the sum. divided by m to take the average. M is the number of samples, and multiply that to the learning rate. Okay, and we are going to do that for all of the data, and we are going to simultaneously update all those weights. Okay, so this part, which is essentially taking the difference between the predicted and the actual and multiplying that by x, is equivalent. This part, this summation part, is equivalent to the error transpose, or error equivalent to this difference and x. So this will be, we can then rewrite it as theta minus the alpha or learning rate times 1 over m times the dot product of error transpose and x. Okay, so I hope that will help you in your implementation. Okay, and so again, after computing the weights, we can simultaneously update the weights, and that will be the new value of weights, and repeat it again until such time that we reach some convergence or the number of iterations that we have set. So while the ordinary least squares minimize the errors in a very specific way by finding the values of b who yield a partial derivative to 0, leading to a closed form formula, or the normal equation for estimating the parameters, the one that has a matrix, the inversion, as you have seen. Gradient descent minimizes the cost function in a very different way. So as you have already seen, gradient descent is an iterative numerical optimization method for minimizing the cost na function and thus finding the parameter na estimates. So the gradient descent does not offer a closed form na formula like the one in OLS, and it is also iterative as it tries to guess the proper values of the parameter that lead to minimizing the cost na function. So note that gradient descent has a different notation for the regression model. So previously, we have this line y equals beta naught plus beta 1x. So in gradient na descent, we use a different notation. Instead of the beta, we use the theta. Okay, and the f hat, we use the h. So remember the MSE. So now, in the previous examples, our problem was to get the beta naught and beta 1, right? So now, since the notation has changed, so our goal is to find the optimal na theta 0 and theta 1, or this theta 0 is the weight of the bias, and the theta 1 is the weight of the first predictor. Okay, and we can do that by using a cost na function. So remember the mean squared na error, and in gradient descent, the cost function is called the mean squared na error, j theta. Oops. So a note on notation, the cost function in gradient descent uses a different notation. Theta instead of d for parameters, and h of x for linear regression model, and j of theta for cost na function. So this is because gradient descent originated from a different na field, and one of the first na algorithms which founded the area of machine learning in applied na mathematics. So that's it.